Welcome! In this session, we'll be exploring problem number 516, longest palindromic subsequence. This problem is a classic dynamic programming challenge that tests your ability to optimize solutions for string manipulation tasks. Let's dive in and break it down step by step. In this problem, we are given a string S, and the goal is to determine the length of the longest palindromic subsequence within that string. To clarify, a subsequence is a sequence that can be derived from the original string by deleting some or no elements while maintaining the order of the remaining characters. For instance, in the string ABC, AC is a subsequence because the order is preserved after removing B. A palindrome, on the other hand, is a sequence that reads the same backward as it does forward, such as Madam or Racecar. The input for this problem is a single string S consisting of only lowercase English letters, with a length ranging from 1 to 1000 characters. The output is an integer, representing the length of the longest palindromic subsequence in the string. To help illustrate, let's walk through some example cases. Take the first example, where the input string is S equals BAB. The output is 4, because one possible longest palindromic subsequence is BBBB, which is derived by removing the last letter A. This subsequence reads the same forward and backward, and its length is 4. In the second example, we have S equals CBBD. Here, the output is 2, as one possible longest palindromic subsequence is BB. While the string contains other characters like C and D, they do not contribute to the palindrome, since order must be preserved. The length of this subsequence is 2, which is the longest possible. Let's consider a third example. For the string S equals A, the output is 1, because the only character in the string, A, is itself a palindrome. Its length is simply 1. Now, let's also think about some edge cases for this problem. If the input string contains only one character, like in the example S equals A, the output will always be 1, since a single character is inherently a palindrome. If the entire string is already a palindrome, such as S equals Racecar, the output will be the full length of the string, because the entire string is the longest palindromic subsequence. On the other hand, if the string has no repeating characters, like S equals ABCD, the output will be 1, as the longest palindromic subsequence in this case would be any one of the individual characters. To solve the problem of finding the longest palindromic subsequence, we first consider the brute force approach. Here, the idea is to generate all possible subsequences of the input string and then check each one to determine if it is a palindrome. Among these, we identify the longest palindromic subsequence. While this method is intuitive, it is computationally expensive because generating all subsequences has an exponential time complexity of O2 to the power of n. On top of that, verifying whether each subsequence is a palindrome adds to the overhead, making this approach infeasible for large input sizes. Instead, we turn to dynamic programming for an optimized solution. Using a DP table, we can track the length of the longest palindromic subsequence for any substring of the input. The key insight here is that if the characters at the current boundaries of the substring match, they contribute to the palindrome. Otherwise, we must consider excluding one of the characters and taking the maximum result from the two possible cases. This approach avoids generating all subsequences and reduces redundant computations, making it far more efficient. The dynamic programming solution has a time complexity of n squared, because we fill an nxn DP table, where n is the length of the input string. The space complexity is also n squared, due to the storage required for the DP table. However, we can optimize the space usage further by recognizing that the computation of DP, I, j, only depends on the current and previous rows of the table. As a result, we can reduce the space complexity to n, by maintaining only 2 rows at a time. This makes the solution more memory efficient. Dynamic programming is chosen as the preferred strategy because it significantly reduces the time complexity compared to the brute force approach. It leverages overlapping subproblems and avoids redundant calculations, making it well suited for this problem. While the space-optimized version is more efficient, it can be harder to implement and debug. On the other hand, the brute force method, though conceptually simple, is computationally impractical for large inputs, reinforcing why the DP approach is superior. The key insight, or aha moment, in this problem is realizing that it can be broken down into smaller overlapping subproblems using the relationship dp, I, j. By focusing on comparing characters at the boundaries of the substring, we can efficiently determine whether to include both characters in the solution or exclude one of them. This realization leads directly to the recurrence relation that drives the dynamic programming approach. Ultimately, dynamic programming, whether implemented with the full table or in a space-optimized manner, emerges as the best strategy. It balances simplicity with computational efficiency, making it capable of handling large inputs up to a length of 10 cubed. This approach not only makes the problem solvable within feasible time and space constraints but also highlights the power of leveraging structure and subproblem overlap in algorithm design. In this problem, we are tasked with finding the longest palindromic subsequence in a given string S. A subsequence, unlike a substring, does not require characters to be contiguous, but their relative order must remain unchanged. For instance, in the string BAB, the longest palindromic subsequence is BBBB, which has a length of 4. To approach this, the first step is to deeply understand the problem and constraints. We know that a subsequence is a sequence derived by deleting some or no characters while maintaining order, and a palindrome reads the same forwards and backwards. A naive way to solve this is to generate all possible subsequences using recursion or bit masking, which, for a string of length n, results in 2n subsequences. Once these subsequences are generated, we can check each of them to see if they are palindromes by verifying if the string reads the same in reverse. However, this approach is computationally expensive and inefficient for large strings. To complete the brute force approach, we would need to track the maximum length of any palindromic subsequence we encounter. By maintaining a variable to store the longest length found so far, we can update it each time we identify a longer palindromic subsequence. Once we have iterated through all possible subsequences, the final value of this variable will give us our result. In terms of implementation, the pseudocode for this approach begins by defining a helper function, is_palindrome, that checks if a string is the same when reversed. Then, another function, longest_palindromic_subsequence, generates all subsequences using bit masking and evaluates each one for the palindrome property. While this method guarantees correctness, its performance is impractical for larger inputs since generating all subsequences alone requires exponential time complexity. The pseudocode continues by updating the max_len variable whenever a palindromic subsequence longer than the current maximum is found. Finally, the function returns max_len as the result. Now, let's analyze the complexity of this brute force approach. Generating all subsequences requires O(2 to the power of n) time, as there are 2n possible subsequences for a string of length n. Checking if a subsequence is a palindrome takes O(k) time, where k is the length of the subsequence. Combining these, the worst-case time complexity becomes O(2 to the power of n*n, which is computationally prohibitive for larger strings. This leads us to the key insight that palindromes exhibit a recursive nature. Specifically, if the first and last characters of a string are the same, and if the substring between them is a palindrome, then the entire string is also a palindrome. This recursive property allows us to rethink the problem and avoid generating all subsequences explicitly. Instead, we can leverage dynamic programming to optimize the solution. Dynamic programming provides an efficient way to solve this problem by breaking it into smaller overlapping subproblems. To do this, we define a 2D array dp where dp, I, j, represents the length of the longest palindromic subsequence in the substring S, ij plus 1. The base cases are straightforward. If I equals j, the substring contains only one character, so it's a palindrome of length 1. If I is greater than j, the substring is empty, so the length is 0. For the recursive relation, if the characters at positions I and j are the same, the length of the longest palindromic subsequence is equal to the length of the subsequence in the substring S, I plus 1 ej, plus 2. Otherwise, the result is the maximum length found by either excluding the character at I or the character at j. To compute this iteratively, we start with smaller substrings and build up to larger ones using a bottom-up approach. This eliminates redundant computations and ensures that we solve the problem efficiently. To implement this dynamic programming approach, we use a 2D table dp where each entry stores the result for a specific substring. This requires n squared space, as the table has dimensions nxn, where n is the length of the string. However, since each state depends only on the previous row, the space complexity can be optimized to O(n) by maintaining just 2 rows at a time. Beyond the data structures, there are additional insights and optimizations to consider. For example, memoization can be used to store intermediate results, reducing redundant computations. While both recursive and iterative approaches are valid, the iterative method is generally preferred due to its simplicity and reduced space usage. It's also important to handle edge cases, such as when the input string is empty, contains a single character, or consists of identical characters. In these scenarios, the outputs should be 0, 1, and the length of the string, respectively. The pseudocode for the optimized dynamic programming approach is as follows. We start by initializing a 2D table DP with dimensions nxn, where each entry is set to 0. The base case is that every single character in the string forms a palindromic subsequence of length 1, so we set dp I equals 1 for all valid indices. Next, we fill the table for substrings of increasing length, starting from 2 up to the length of the string. For each substring, if the characters at both ends are the same, we add 2 to the result of the inner substring. Otherwise, we take the maximum result from excluding either the leftmost or rightmost character. Finally, the length of the longest palindromic subsequence is stored in dp 0 and 1, which represents the entire string. This approach ensures that we calculate the result efficiently while avoiding unnecessary computations. Analyzing the complexity of this optimized dynamic programming approach, the time complexity is O(n) squared, because we iterate through all substrings of the input string, and for each substring, we perform a constant amount of work. The space complexity depends on the implementation. A full DP table requires O(n) squared space, but with space optimization, this can be reduced to O(n) by maintaining only 2 rows. This trade-off makes the approach highly efficient for practical use. By leveraging the recursive nature of palindromes and the principles of dynamic programming, we can solve the problem within feasible time and space constraints, even for relatively large strings. This implementation solves the longest palindromic subsequence problem using dynamic programming. The goal is to find the length of the longest subsequence in a string that reads the same forward and backward. We start by initializing a 2D DP table DP where dp ij represents the length of the longest palindromic subsequence in the substring s, ij plus 1. The table is initially filled with zeros. Single character substrings are palindromes of length 1, so we set dp I equals 1 for all valid indices I. Next, we fill the dp table for substrings of increasing lengths, starting from 2 up to the full length of the string. For each substring defined by its start index I and end index j, we check if the characters s, I, and s, j match. If they match, the palindrome length extends by 2 beyond the length of the subsequence within s, I plus 1 ej, so dp I, j equals dp I plus 1, j1, plus 2. If they don't match, we take the maximum length by excluding either s, I, or s, j, so dp I, j equals max, dp I plus 1, j, dp I, j1. Finally, the result for the entire string is stored in dp 0 and 1, which we return. This approach ensures an optimal computation with a time complexity of O(n) squared and space complexity of O(n) squared, where n is the length of the input string. The code efficiently handles edge cases like empty strings or strings with no repeating characters, ensuring correctness and robustness. Here, we're looking at the implementation of finding the longest palindromic subsequence in a given string using dynamic programming. First, we define a class called solution and a method longest palindrome subsec that takes a string s as input. We initialize a variable n to store the length of the string and create a two-dimensional dp table, dp, initialized to 0. This table will help us store the results of subproblems to avoid redundant calculations. Next, we handle the base case. Single character substrings are always palindromes of length 1, so we iterate through the diagonal of the dp table and set dp I to 1 for all indices. After handling the base case, we proceed to fill the dp table. We use a nested loop structure. The outer loop iterates over different substring lengths, starting from 2 and going up to the length of the string. The inner loop iterates over the possible starting indices of these substrings, calculating the corresponding ending index as j. For each substring, we check if the characters at the start and end indices match. If they do, we extend the palindrome length by adding 2 to the result of the smaller substring dp, I plus 1, j1. If the characters don't match, we take the maximum value between excluding the start character or the end character, which is math.max, dp, I plus 1, j, dp, I, j1. Finally, after filling the dp table, the result for the entire string is stored in the top right corner of the table, which corresponds to dp, 0, and 1. This value represents the length of the longest palindromic subsequence. We simply return this value as the result of the method. This implementation ensures that we efficiently compute the solution by breaking the problem into smaller overlapping subproblems and solving each only once. With a time complexity of O(n squared) and space complexity of O(n squared), this approach is well suited for moderate-sized inputs. To solve the problem of finding the longest palindromic subsequence, we start by initializing a 2D dynamic programming table, or DP table, with dimensions based on the length of the input string. For the example input s equals bab, the string length is 5, so we create a 5x5 table initially filled with zeros. This table will help us systematically store the lengths of palindromic subsequences for different substrings. Next, we handle the base case. Single-character substrings are always palindromes of length 1, so we set all diagonal elements dp, I, to 1. This reflects the fact that each individual character in the string forms a palindrome by itself. The updated table now has 1s along the diagonal, and this forms the foundation for filling out the rest of the table based on longer substrings. Now, we begin filling the dp table for substrings of increasing lengths, starting from length 2. For substrings of length 2, we compare the characters at the boundaries s, I, and s, j. If they are not equal, we take the maximum value between excluding either the left or the right character. In this example, for I equals 0 and j equals 1, since s, 0, equals s, 1, we compute dp, 0, 1, as the maximum of dp, 1, 1, and dp, 0, 0, which results in 1. Moving to length 3, we again compare the boundary characters. If they match, as in the case of I equals 0 and j equals 2, where s, 0, equals s, 2, we add 2 to the value for the inner substring, dp, 1, 1, resulting in dp, 0, 2, equals 3. This process continues as we calculate values for all substrings of increasing lengths, systematically building up the table. By the time we process all substring lengths, we end up with the final dp table. For the given input s equals bab, the table now contains all the necessary information to determine the length of the longest palindromic subsequence. The top right corner of the table, dp, 0, and 1, gives us the result, which is 4. This value represents the length of the longest palindromic subsequence in the string. Moving to the next example, with input s equals cbbd, we initialize a new dp table of size 4x4 since the length of the string is 4. As before, we start with all zeros, preparing the table for processing substrings of increasing lengths. Once again, we handle the base case by setting all diagonal elements of the dp table to 1, as single-character substrings are palindromes of length 1. With this base case in place, we begin processing substrings starting with length 2. Here, for I equals 1 and j equals 2, the characters s, 1, and s, 2, are equal, meaning the substring forms a palindrome. In this case, we add 2 to the value of the inner substring, which is dp, 2, 1, so dp, 1, 2, equals 2. We continue this process for longer substrings, ensuring that we evaluate each pair of boundary characters and fill the table accordingly. This systematic approach ensures that all possible palindromic subsequences are accounted for and their lengths calculated. After processing all possible substring lengths, the final dp table for the input s equals cbbd is complete. The top right corner of the table, dp, 0, and 1, gives us the result, which is 2. This indicates that the longest palindromic subsequence in this string has a length of 2. As a final example, consider the string s equals abcd. Since no characters in this string match, the longest palindromic subsequence is simply any one character, resulting in a length of 1. This demonstrates that the approach works for all cases, regardless of whether the string contains matching characters or not. To analyze the time complexity of the solution for the longest palindromic subsequence problem, we start by breaking down the operations. First, we initialize a 2D dynamic programming table, or DP table, to store intermediate results. This table has dimensions of n*n, where n is the length of the input string s. Since we need to fill every cell with zeros during initialization, this operation requires n² time. Next, we handle the base cases. Specifically, we set the diagonal entries of the table dp I to 1, as any single character is itself a palindrome of length 1. Since there are n diagonal entries, this step takes n time. These two steps set the stage for the main computation of the algorithm. The next part of the algorithm involves filling the dp table for substrings of increasing lengths, starting from length 2 and incrementing up to n. For each substring length, we iterate over all possible starting indices I. The ending index j is determined by the formula I plus length 1. At each step, we compare the characters at positions I and j. If they match, we add 2 to the value of a smaller subproblem, which is dp I plus 1 j1. Otherwise, we take the maximum of 2 other subproblems, dp I plus 1 j and dp I j1. Since there are n*n cells in the dp table and each cell is computed in constant time, this computation requires n² time. Combining this with the initialization and base case setup, the overall time complexity of the solution is n². Now, let's discuss the space complexity of this solution. The primary contributor to space usage is the dp table, which is a 2D array of size n*n. This means it requires n² space. Additionally, the algorithm uses a small number of auxiliary variables, such as n, I, j, and length, to manage loops and intermediate computations. These require only O1 space. Since the storage required by the dp table dominates the overall usage, the total space complexity is n². This is a reasonable trade-off for the significant time optimization provided by the dynamic programming approach. To better appreciate the efficiency of the dynamic programming solution, let's compare it to a brute force approach. A naive solution would generate all possible subsequences of the string s and then check each one to determine if it is a palindrome. The number of subsequences of a string of length n is 2*n, and checking if a subsequence is a palindrome involves n time. This results in an overall time complexity of n*2 to the power of n, which is exponential and impractical for large inputs. In contrast, the dynamic programming approach avoids redundant computations by breaking the problem into overlapping subproblems and storing intermediate results. This reduces the time complexity to n² and the space complexity to n². It's also worth noting that the performance of the dynamic programming solution remains consistent, with a time complexity of n² in the best, average, and worst cases, as the algorithm always processes all possible substrings regardless of the input string structure. Finally, let's solidify our understanding of the algorithm's efficiency with a mathematical proof for its big O complexities. The dp table consists of n*n entries, and each entry is filled in constant time, giving a total time requirement of n². Similarly, the memory usage is proportional to the size of the dp table, which is also n². Since there are no additional hidden costs or factors that could affect the asymptotic bounds, we can conclude that the dynamic programming solution is both optimal and efficient for this problem. It provides a dramatic improvement over the brute force approach, making it well suited for handling larger inputs. When tackling the longest palindromic subsequence problem, there are several common pitfalls to be aware of. First, always account for edge cases, such as when the input string is empty. Neglecting to check for this can lead to runtime errors. Next, it's important to distinguish between substrings and subsequences. A substring is a contiguous section of the string, whereas a subsequence maintains the order of characters but doesn't need to be contiguous. Misunderstanding this distinction can lead to incorrect solutions. Another frequent mistake is relying solely on the brute force approach. While conceptually simple, it has a time complexity of 2 to the power of n, which is infeasible for larger strings. Dynamic programming can significantly optimize performance in these cases. Additionally, in recursive solutions, improper base cases such as forgetting to handle strings of length 0 or 1 can lead to infinite recursion or erroneous results. Lastly, while designing a dynamic programming solution, be mindful of space complexity. A common approach uses a 2D table of size n*n, which can consume a lot of memory. To mitigate this, consider space-efficient techniques like using a rolling array. Now, let's consider some insights that can help you approach this problem effectively in an interview setting. The problem benefits from an optimal substructure, meaning it can be broken into smaller subproblems, such as finding the longest palindromic subsequence for smaller substrings. This makes it a perfect candidate for dynamic programming. Additionally, palindromes are symmetric around their center, and leveraging this property can help eliminate redundant computations. When comparing approaches, brute force might be simple to conceptualize but is rarely practical for longer strings. Dynamic programming strikes a balance between clarity and efficiency, while recursive solutions with memoization are often preferred in interviews due to their simplicity and optimal performance. Finally, always clarify the problem requirements when discussing variations. For example, some versions of this problem might ask for the count of distinct palindromic subsequences instead of just the longest one. Ensuring you understand the specific requirements is critical to providing the correct solution. This problem is closely related to several others that can deepen your understanding of palindromes and dynamic programming. For instance, the longest palindromic substring problem focuses on substrings rather than subsequences and is a great way to practice working with contiguous parts of a string. The longest common subsequence problem is another related challenge that shares a similar dynamic programming structure, making it highly useful for grasping subsequence-related techniques. For those looking to tackle more advanced variations, the count different palindromic subsequences problem involves identifying and counting all unique palindromic subsequences, which is significantly more complex. Lastly, the palindrome partitioning problem shifts the focus to splitting a string into palindromic segments, offering yet another perspective on working with palindromes. Finally, let's explore some alternative approaches to solving this problem. The most commonly used method is dynamic programming, where you define a 2D table dp, I, j, to store the length of the longest palindromic subsequence between indices I and j. This has a time complexity of O, n squared, and a space complexity of O, n squared. A recursive approach with memoization is another option, where you solve the problem by considering whether the first and last characters of a substring are part of the solution. By memoizing results, you avoid redundant calculations across overlapping subproblems. For an iterative, space-optimized solution, you can use a rolling array to store only the previous row of the DP table, reducing space complexity to O, n. While some may attempt a greedy approach, this is generally not recommended, as it often fails for more complex cases and is not a robust strategy for interviews. Great job! We've covered problem number 516, longest palindromic subsequence, and explored the dynamic programming approach to solve it efficiently. Remember to practice similar problems to strengthen your understanding of DP concepts. Thanks for watching, see you next time. That's the end of this tutorial. I hope you found this explanation helpful for understanding the solution to this LeetCode problem. If you enjoyed this content, please consider subscribing to the channel for more coding tutorials and solutions. Feel free to leave a like if this video helped you, and don't hesitate to comment with any questions you might have. Thanks for watching, and happy coding!